you everyone for coming. Good to see you all. I'm Callum Shakespeare. If you don't know me, I'm the Honours Convener here at the School of Earth Sciences. I'm kind of opening this on behalf of Louis University, who's the Associate Director of Education, who couldn't be here today. So we're basically here to tell you all about the wonderful opportunities to do research in the School of Earth Sciences. Earth Sciences is really a very interdisciplinary school. So we have lots of people come to do research who might come from physics or maths or environmental science or chemistry or biology or computer science, engineering, anywhere across the university. All of those things are a great background to come and do projects in the School of Earth Sciences. And we have many options for projects at different levels, starting in undergraduate research. So as part of RSES or special topics, you're very welcome to come and do a semester of research with us. Honours, which I'm responsible for, masters, and then also high degree research. And the administrative contacts for each of those are there. So today we'll be more talking about the actual research rather than the technical details. But if you have questions about how do I get into this, then please reach out to these addresses or talk to me or any of the others here afterwards as well. So we're going to go through with presentations. I think we have about different presentations about from different parts of the school about the research that's going on and how you can contribute. And then there'll be a chance for some questions at the end. And we need to finish on the hour because there's an AGM for the Marine Science Society happening in the room afterwards. Okay, Megan is that.
Okay. Hi, I'm Megan Miller. I'm a seismologist. I think I know a few of you, but many of you I have not met before. So I'm going to talk a bit about kind of two main themes of the research that I do. So I trained as a seismologist. So I was mostly interested in plate tectonics, and that's what I did during my education. So this is a nice map of all the earthquakes and also the vectors showing plate tectonic motion. So those are still like kind of the primary thing that me and my research group are interested in, is understanding how the Earth has evolved through time, and we do that using earthquakes. And so some of the scientific questions that my group is interested in, basically structural seismology. So you can see the match between structural geology and also seismology. I want to know about how plate tectonic systems evolve, how we can image the subsurface in high definition, whether that's below volcanoes or faults or the whole subducting plate, actually even all the way down through to the core, and how can we improve detecting earthquakes. And so I mostly do this by doing field work, and I go out and put seismometers in strategic locations. This is a picture of me on a glacial moraine in Alaska, putting out a seismometer. And so I currently have projects in WA, in Indonesia, New Zealand, and Alaska that are available for student projects. I also do a lot of photonic seismology. So I've kind of transitioned recently to look at different types of instrumentation to record data in a different way. And this is by using fiber optic cables to detecting ground motion using light. So instead of using a traditional seismometer, we use fiber optic cables. And the technique that I usually use is called distributed acoustic sensing, or DAS. And this repurposes telecom cables, so the cables that we use to get our internet, into seismic sensors. And we can do new scale measurements at about a meter scale, so very different than the traditional methods. And how that works, you can see that this fits into physics, so optics, engineering, seismology, tectonics, many different fields. So we use an instrument called an interrogator. We connect this to fiber optic cables, so the ones that are plugged into here. We send a laser pulse from the instrument, and it's at a very, very, very high frequency, so tens of thousands of hertz. And then we measure the laser pulse when it comes back in this box. And so when there's a disturbance in the ground, whether that be an earthquake or a volcano erupting or our feet walking over a cable, this perturbs this phase of the light, and it comes back and we measure this delay time. And so we can do that to infer lots of different earth processes, whether this be an earthquake. We can also see changes in aquifers. We can look at tsunami waves. We can look at volcanoes. We can look at traffic. We can measure thunderstorms. So lots of different applications in the earth sciences. And so some scientific questions that use DAS Can we monitor river systems? So those are kind of environmental seismology rather than structural seismology. Can we detect storms in the oceans, in the atmospheres, rivers? Can we improve detecting and monitoring landslides? This is work in New Zealand. Can we aid in monitoring avalanches? So those are the types of projects that I have available. And these are field-based projects in New Zealand, Australia, and Hawaii. And that's it.
Hello, everyone. I'm Caroline Eakin. You haven't met me already. And similar to Megan, I'm also an observational seismologist. And what that means, observational seismologist, is I go to geologically or tectonically interesting places, like this example here in Central Australia in the Simpson Desert, install and deploy passive seismometers that record seismic waves generated from, for example, earthquakes, and locally and globally, to then image the earth below. So why is observational seismology important in Australia? One of the reasons is that almost 3/4 of the Australian continent is covered by sediment and regolith, and this provides a mask obscuring the continent below, hindering our understanding of the deeper structure of the earth. So if you want to know more about the tectonic history and evolution of our continent, if we want to know where valuable mineral systems, such as critical minerals, are buried beneath the continent, we want to understand more about seismic hazard, so the faults and major tectonic boundaries where earthquakes occur, thickness of the sediment themselves, understand seismic hazard and shaking, then we need geophysics and we need seismology to see beneath this sediment. So ANU over the past several decades has led the charge at deploying passive seismic instruments over Australia. As you can see, there's some parts of the Australian continent which are well covered by these instruments, as seen on the map, and there's some parts which are still quite sparse. So that means there's still quite a lot to do in this space. I've highlighted 2 current projects that are ongoing that myself and other colleagues at RSES are involved in. First is SNAKY, the blue dots here, stands for Seismic Network around Kangaroo, Eyre and York Peninsulas. This is looking at seismicity, crustal and lithospheric structure along the southeast margin of the Golar Craton, where we have quite a few earthquakes and also some important mineralization. Another really exciting project happening right now is the WA Array. This is being led by the Geological Survey of Western Australia, but we're involved as academic partners. And over the next decade, these purple dots, they're going to cover the entire states of Western Australia with seismometers at 40 kilometers spacing. So by the end of this, in the next 10 years, it will be one of the largest continental scale arrays in the world. So using these data sets, and many exciting projects and opportunities to study the Earth using these data sets, range of topics from looking at the earthquakes themselves, how interplate earthquakes occur in Australia, understanding more about the tectonic boundaries, crustal lithospheric structure, and the dynamics below the Earth. In seismology, we're often looking for people with some kind of quantitative background, whether you've come through earth science and done geophysics, or you're people for physics, astronomy, or engineering backgrounds, something like that. Having some prior coding experience doesn't need to be a lot, but something is very helpful in order to be able to work with the data. So it's a lot about handling data, plotting waveforms, time series analysis, those kind of skills. All right, thank you.
Okay, so I'm Greg. I know some of your faces from last semester and previous years. I'm in the geochemistry research area in RSES, and specifically in the experimental petrology group. And one of the major focuses of our group in terms of our research is around critical metals. And you would have heard a lot of media recently involving Albo going to visit Trump and signing an $8 billion critical metals deal between the US and Australia, which is supposedly going to really benefit our economy and our critical metals industry. It's a very hot topic. Critical metals are those metals which are used in high-tech applications such as wind turbines, magnets, electric vehicles, batteries, phones, computers, you name it. Just about every device that you use contains critical metals. And so a lot of our research is to try and understand how deposits of these critical metals form, how we can find them, and to understand how these metals get concentrated to economic grades in these deposits. Now, one of the largely neglected minerals that is involved in this is magnetite, which forms in a rock type called carbonatites. And so this particular project that I'm going to talk about is an honours, maybe master's level project, looking at how magnetite forms and what it tells us about carbonatites. But there are many other projects in this critical metal space that we can come up with. So carbonatites are possibly the weirdest rocks on the earth. They're igneous rocks, with one notable exception. They're plutonic, so they're intruded into the Earth's crust, where they crystallise from a magma. There's one example of an erupting carbonatite on Earth at the moment. That's Aldonio Lindai, which is in Tanzania. But all other carbonatites are in the geological record past. Okay? Now, they're mineralogically quite complicated, but essentially they're made of carbonate minerals predominantly. They're not like a gabbro or a basalt. They're not made of silicate minerals, but they're primarily made of carbonate minerals. But they contain a lot of other interesting minerals, some of which are sources of things like rare earths, in the case of all of these, very strange named minerals, or in the case of pyrochlore and niobium, for example. Magnetite is not so much of an ore mineral, but it's a mineral that indicates something about the magnetic evolution of carbonatites and tells us something about how they might fractionate in the crust, leading to enrichment in rare earth elements, which are all written along the side of this taxi, which I was very enthusiastic to see in Oxford many years ago. So the rare earths are really important, and carbonatites are a major source of rare earths over the world. And in Australia, we have Mount Weld, which is a huge carbonatite out in the Yilgarn Craton. That's the only one in Australia that's been mined for rare earths at the moment, but that is a very significant resource. And so it's not actually part of Trump's deal, but nevertheless, it's a very large rare earth deposit. So understanding magnetite, well, magnetite is a mineral which contains iron in both of its oxidized forms, so ferric iron and ferrous iron together. And so if we're going to study it experimentally, we need to understand, or we need to be able to control the oxygen state, or the oxygen oxidation reduction state of our experiments. So this is an experimental project where we will determine how magnetite forms from carbonatite magmas. And then we would also measure some addition coefficients of trace elements between the melt and the magnetite, which would help us to track the evolution of the carbonatite. And we would use presses like this one, piston cylinder press, which we have a whole bunch of upstairs in Jager 1, and analysis using electron microscopes and which can analyse the chemistry of the minerals that we produce in these experiments. I mentioned we have to control the oxidation or reduction state of the experiments, because right up here we have hematite, where all the iron is in a ferric form. Down here we have wustite, iron wustite, and so below this all the iron is in metal form. This is the oxidation state. This is oxidized and this is reduced. We need to land in here where magnetite will be stable, and we can do that using chemical buffers in our experiments. So as well as controlling pressure and temperature, we can control the oxidation reduction state of the experiments, and therefore hopefully land in the right place to actually crystallize tons of magnetite from these experiments. We'd add some trace elements to it, and then we'd be able to model the evolution of the carbonatite as it crystallizes, at least as it crystallizes magnetite. And then we can apply that information to Mount Weld, Australia's biggest carbonatite, because we have plenty of magnetite crystals from there. We can measure their compositions and see that how they compare with the significant experimental results. And these are some of the traceabilities. So that's just one kind of fairly specific example of a project. But if you're interested in critical metals generally, and particularly in carbonatites, there are many other similar sorts of projects that we can come up with to try and understand the behaviour of these rather unusual systems. Okay, thank you.
Hi, I'm Adele Morrison, for those of you that don't know me. I'm an ocean modeler, and so that means I run these high resolution models on the supercomputer Geodesy and ANU and try and understand the ocean circulation and how things might change in the future for the oceans and climate. So in particular, a lot of my research focuses on the Southern Ocean, that you can see here. And the reason for this is that it's really important. So the Southern Ocean contributes about 70% of the total global ocean heat uptake, of the excess heat from climate change. And also the ice loss from the Antarctic ice sheet at the moment is being driven pretty much all by ocean warming around Antarctica. But despite how important this is, there's still so much we don't understand. So in particular, if we look at projections of Southern Ocean heat uptake into the future, between the different climate models, those projections differ by about an order of magnitude. And the sea level rise from Antarctica, that's currently the largest contributor to the uncertainty of our sea level projections this century. So we need to understand the processes by which the ocean is changing and controlling heat uptake sea level to have better projections. So listed here just a few examples of possible projects, but there's a lot of other options as well. So trying to understand the processes, so different circulation and mixing changes in the ocean that are controlling the Southern Ocean heat and carbon uptake. So if we look at projections, we can say which ones might be more accurate than others. So there's been a large decline over the last 10 years or so in Antarctic sea ice, understanding what that's doing to ocean heat transport towards Antarctica. And then another one, understanding, so when Antarctica melts, it puts meltwater into the ocean around Antarctica, and this changes the ocean circulation. Then try to understand how those changes in ocean circulation then feed back on that ice melt. See if that results in more or less ice melt into the future. Best background for this kind of work are quantitative skills, so background in physics, maths. We have a couple of climate science courses that are very useful background in earth sciences, and a lot of what you'd actually be doing in these projects is data analysis using Python of output from these high resolution ocean models. Thanks.
Okay, me again. So continuing the climate and fluid physics theme. So Adele, myself, and Kyle, who's coming next, are all in this climate and fluid physics field. Like Adele, I also do quite a lot of ocean modeling, but I focus on either smaller or faster scale processes. Let me see if I can get this movie to play. I'm not sure I'm interested in the plays. No, yes. Excellent. So one of those faster processes is the ocean tide. Now, if those of you who go down the coast, you might look at tide charts like that at the top. And if you're starting at the coast, all you see is the tide going up and down on the coast each day. But really, that coastal signal is part of this global wave that's propagating around the world ocean. And you can see your tide here at the coast, that Batemans Bay is connected with the tide everywhere else. And the magnitude of that tide you're seeing at Batemans Bay is actually dependent on all these interactions that are happening elsewhere in the world ocean. You probably all know the tide's forced by the moon predominantly, and a little bit by the sun. And that's how it gains its energy. And then it loses its energy when it rubs up against the seafloor throughout the world ocean. And this is what happens when it rubs up against the seafloor. So it triggers, it hits these undersea mountains, sloshes backward and forward over it, and triggers these features that propagate out. So these are wave signals that are inside the ocean. So the signal you're seeing there is the stratification of the layers in the ocean sloping up and down over time. And they generate these waves that propagate thousands of kilometers across the ocean. There's a particularly big one here from Macquarie Ridge that smashes into Tasmania. And so these waves that are generated, they control the energy that's coming out of the tide, and therefore they control the amplitude of the tide. They also provide the energy that mixes up the ocean. And so if you want to understand what's going to happen in the future with carbon and heat being sequestered in the ocean, you need to understand the mixing that's done by these propagating waves. They also, as they propagate through, interact with the eddy field that you saw in Adele's lovely movie, and it's also here. And because these eddies have this three-dimensional structure, so this was a warm eddy, it's got some current around it, and waves can propagate into this and interact with it. And that's also another complication, this sort of story of how energy cascades through the ocean. So in terms of possible research projects, a few specific ones is thinking about how these tides interact with topography and how that varies seasonally. So there's a good example in the Luzon Strait, which they call the tidal seesaw. So the Luzon Strait is like Taiwan, and these waves that are being generated, they go in one direction in one season and another direction in the other season. No one really knows why. Very interesting problem there. There's a lot of questions around how these waves interact with eddies. And then there's a very interesting question about the sensitivity of your coastal tides to environmental conditions. So if anyone's been to Lakes Entrance, anyone been to Lakes Entrance, Gippsland? Yep. So they did some dredging in the channel there, the mouth of the estuary, and they managed to change the tide, enhance the tide in the estuary and started flooding the town. Okay. They raised it by about, the tidal range came up by about 30 centimeters. Okay. And so you can change small things around the coast and that can have a huge impact on the coastal tide. And those are the sort of things I'm also interested in understanding. In terms of methods, a lot of numerical modeling on the supercomputer. This could be using established ocean model codes, or it could also be about developing some simplified models that you could solve in a Python script or MATLAB. Background very much physics, maths, engineering, coding, that kind of stuff. And I have one more slide on behalf of Kiara, who couldn't be here. So Kiara is our resident rainfall expert. So the picture you're seeing here is from a climate model showing you rainfall, both liquid rainfall in the green yellow colors and frozen, the snowfall or ice in the blue. And you can see rainfall, for example, over Australia, comes in these events, you know, in these distinct front systems. We had one yesterday come through, which you'll appreciate it, I'm sure. And Kiara is interested in understanding how these things operate, how they bring rainfall, and particularly how they're changing under climate change. So she's part of the 21st Century Weather Centre of Excellence, and she's got a number of projects at the moment around the weather system, how that changes are affecting freshwater supply. She's also an expert in drought, and so she's looking at can climate models simulate drought, because that's been historically a big issue. And also thinking about hydropower potential into the future and how the weather system changes might impact that. So she's looking for people with atmospheric science or hydrology, or depending on your level, that could just be that sciences, maths, physics, climate background as well.
Thanks. Leave that slide up actually.
Leave that up? Yep.
Yeah, because this is actually a really good segue. So I'm Kyle. And these things that Callum was pointing to, that what I mean, these events that are bringing a lot of rain over Australia are actually, these are Rossby waves. So you kind of see that this, if you squint your eyes and kind of trace them out. There's the phase is set by the Andes here, so trying to squeeze underneath the Andes. Maybe 5 or 6 of them, depending on the season bring. So these are Rossby waves. And the majority of Australia's weather is that is experienced by the majority of Australians. They're actually is set by these waves, and you kind of see that they're coherent and they're moving, they're sweeping. So why do we get weather so bad? Why aren't we able to predict it as well as we should be able to, given that we can see these events coming from days out? And part of the problem is the scale at which we need to actually be able to resolve these or predict these features in our weather simulations is just enormous. Like these events are like these waves are the size of the country, but yeah, that's the scale at which they manifest and which they propagate at. But the scale on which they're actually breaking and sort of generating weather is tiny. It's like, you know, maybe kilometer or 10 kilometer scale. So you actually need a numerical simulation that's able to capture something that's, you know, 10 or 30 or, you know, the planetary scale, like 10,000 kilometers, right down to something that's like 1 kilometer. And so the numerical cost of that is extraordinary. And you certainly aren't able to use something like that to understand the dynamics of this in a way that we can if we were to run it in a lab. So we've got Australia's only physical model for Rossby waves in the climate and fluid physics lab, and we're actually using that to better understand those Rossby wave dynamics and what happened, well, yeah, how they're breaking, that sort of thing. These waves, these little features that you're actually seeing in the rotating table at the moment are not Rossby waves. These are sort of geostrophic eddies. And this is another project that we can run in the rotating table. One where we actually see passive tracer like particles throughout the annulus. The table itself is probably 1.6 meters across, so it's quite large. And these little particles, these are passive tracer that are actually in the fluid that are moving around with the fluid, showing us where they're actually going. And then what I've overlaid over the top of that is an image from a thermal camera, which is recording the surface temperatures as well. So you can kind of see that the particles themselves move along the isotherms. They're moving with the gradient of temperature, which is telling us that this flow is actually geostrophic. So this is when you look at a weather map and the wind is blowing along the isobars, the lines with pressure. In the lab, they're isotherms. So that's what we're actually seeing here. And one of the projects that we've put together at the moment is trying to figure out, like, if we're able to see the surface temperature, can we actually infer what the velocity field is? You know, basically, you know, here we can kind of, you know, we just track the particles and actually sort of get the velocity field out of that. But if we didn't have the particles, if we only had the temperature, can we actually invert that to get the velocity field? And where that's useful is we've got a lot of very high resolution satellite images of surface temperature of the ocean, but we don't have particles in the ocean. So are we able to actually see the ocean velocity field on a scale that we can actually measure from satellites? That's one of the projects that we're working on in the lab. And I've mentioned the first one, which is the Rossby waves in straight weather, and another one would be a very long tank, maybe 6 meters long, in which we're sort of exciting interfacial waves by blowing wind over the top of the tank. And this is a laboratory model for the El Nino Southern Oscillation. I think that's probably I'm not sure who's next. Paul.
And the consequences of weather are rainfall or lack thereof. And that goes into what we can measure with satellites. So I'm a geodesist. My work is done using remote sensing satellite data to study things on the Earth. So the way I decided to cover the whole plethora of things that we can do in our group is just to show some of the projects that are going on at the moment. We have a master's student who will be starting a research project next year, looking at what we're calling the big blue blob up in Northern Territory. So this is about, this is from space gravity data from the Grace Solomon mission. It's about 600 millimeters of extra mass of water in the Northern Territory, spread over about 1,000 kilometers. And yet there is no surface lake. There's no massive growth of vegetation. Groundwater bores are not showing a significant increase. So what is this extra increase in mass? It's either a mistake by the satellites, the mission is not working properly, or there's water in the system somewhere. And so it's going to be an interesting project to work out where it is. There was nothing there in December 2022. Cyclone came across, it's basically stayed very dark blue through until 2025, and it's starting to weaken a little bit now. So there's water there somewhere. We need to find out where it is. The next project is using the SWOT mission, Surface Water Ocean Topography. This is a satellite that can measure the height of water accurate to about 5 centimeters on about a 40 to 100 by 100 meter sort of scale. Lachlan Dodd has looked at the depth of floodwaters that flow down in Western Queensland and has been the water that's filled up Lake Eyre, which is full at the moment. We've also looked at the Pakistan flood that happened a couple of months ago. This one killed over 1,000 people and had a massive economic disruption to Pakistan. This one killed 3 people, but about 100,000 sheep and cattle. And is very valuable actually for the Lake Eyre ecosystem. So totally destructive flood over a small scale. It's not very deep. This is like a meter or 2 deep. Very deep. This is up to 10 meters, massive amount of water coming through into Australia. So there are projects about the ecosystems and extremes of floods. Another project using SWOT is looking at environmental flows to endangered wetland systems. So because of this satellite, it's a new satellite system, it's only been up a couple of years, we can now measure water depth in wetlands and valuable environmental systems in a way that we've not been able to do before. So all the ungauged rivers in Australia can now be measured. All of the endangered and very fragile ecosystems can be studied because we can know how much water is going into those systems. A more typical sort of project, solid earth one, is glacial isostatic modeling in Antarctica. We need to know how much the land is currently uplifting and increasing the strength of the gravity signal so that we can subtract that and be left with the mass loss of Antarctica, which is contributing to global sea level, which was the problem that Adele mentioned. Possible research projects, an assessment of extreme floods and droughts. So Grace can quantify these sort of things. SWOT can measure the amounts of water. We also have soil moisture missions that can tell us how much is or is not in the soil. The availability and allocation of water resources across Australia comes again from those sorts of missions. This is observational science, so we can quantify what's actually happening, and that informs policymakers or it can show the consequence of certain policies. We can look at stream flows of ungauged rivers because we now have techniques that can detect this sort of thing we couldn't before. We can look at sea level rises around Australia. I just picked an example here. This is actually San Francisco, measurements from the SWOT mission, and it's showing centimeters or decimeter sort of level changes in the ocean height in that area. So we can use this, excuse me, to look at nearshore increases, and we could study the consequences of dredging in the Gippsland area because you could measure very accurately the height of the water in that area. We can look at determining flood depth for emergency services during flood disasters. Now, you probably remember the Lismore floods over the past few years. It turns out that the available gauges in that area haven't worked for some years and still don't work, some of them. And river gauges only tell you the depth of water in the river when they're working, but the houses that are flooded are not in the river. They're across on the paddocks. And so we need to know the flood depth, and emergency service workers need to know which people they need to go and save first, which ones are at greater risk. We can do this now with satellite data. Projects can be honours, masters, PhD level. It can be specifically technical about the satellite instruments and how they operate and how to make them give better data. It could be processing that data for a particular application to study some particular effect. It could be a more sort of abstract connection to the satellite data for example, migratory patterns of birds, where the birds are going to obviously fly in places where there's food and water for them. We can quantify what's on the surface of the earth at any given time and correlating that with migration patterns like this. Okay, I'll leave it there.
So, hi everyone, my name's Dave. I think I've taught quite a lot of you before. Maybe plate tectonics, maybe applied geophysics, maybe natural hazards, none of which I actually do research in. So here's what I do research in, okay? And it's specifically old iron. And I'm going to be talking about a series of topics that I do research in. I'm not going to be mentioning specific potential projects, but rather, if any of these themes sound interesting to you, just come and have a chat, and we can normally find something that's going to fit your skill set into the kind of research questions that we're addressing. Okay, so this is a very broad overview. And it's going to go from an atomic to a planetary scale. So one of the things I do work on is magnetic mineral physics. So when I say iron, the main thing that I'm interested in with respect to iron is that it's magnetic. Okay, so Greg has already mentioned magnetite as a strongly magnetic mineral, and we're interested in why these minerals are actually magnetic and their behaviors. Okay, and to do that, we need to look at magnetic mineral physics, and you'll see why that's important as I go through some of these topics. The next one is the evolution of these things called magnetotactic bacteria. So I've got a little movie. This is a water bubble under a microscope. Okay, and you can see these little sausage shaped things here. These are bacteria, and they're experiencing a magnetic field, which is the direction of the magnetic field is shown by this white line here. So assuming that the technology is going to work, what you'll see, they're swimming around in this water bubble, and we change the direction of the magnetic field, they all swim in the opposite direction. Quick track them forward. Yeah. In a moment, we'll get them going in circles. Yeah. All right. So these are common in the environment. We didn't think they were, but about 10 or 15 years ago, we came up with a new technique for detecting these things, and now we find them absolutely everywhere. Okay. And so we're really interested in them for a number of reasons. First of all, from an evolution point of view, how did these things form? Okay. They're using the Earth's magnetic field for navigation. So that must mean when they did form, the Earth had a magnetic field. They typically contain magnetite, but it might be some other mineral. So what controls that? And it also, when we find them in lakes and oceans, they're also the species that we have also tells us about the environment. So some like warm water, some like cold water, some like lots of oxygen in the water, and so on. So by studying these things, we can make environmental reconstruction, but we also find something out about bacteria that can also tell us about the history of the Earth's magnetic. So that's a big thing that I've been working on for around the last 10 years. Slightly different thing, iron ore. Okay, so obviously the world has a problem with carbon emissions and climate change, and about 8% of the carbon emissions come from steel production. And we don't have a scalable alternative to steel. So we're going to need to keep making steel. Technologies have come along now that means we can really reduce carbon emissions from steel production. But to do that, you need high quality iron ore, by which I mean it contains a lot of iron. And most of the iron ore in Australia doesn't contain enough iron. So we have to try and work out a way to increase the iron in the iron ore. This is called beneficiation. So one of the big advantages of iron minerals is they're magnetic. So you can use magnetic techniques to try and pull out the iron-rich minerals and leave behind stuff that doesn't contain iron, called gangue minerals, and therefore increase the grade of this iron ore, which ultimately is going to help us to reduce carbon emissions. Okay, so that's another big thing I'm working on at the moment. Now, the last picture was WA. This is the surface of Mars. Probably not too dissimilar to each other. Okay, so again, when you look at a lot of planetary surfaces, rich in iron minerals. So here we have hematite, we also have goethite, which is an iron oxide hydroxide, that's giving it the yellow-red colour. And iron is very sensitive to redox conditions. So if we can work out what type of minerals are here, that tells us something about how the surface formed. Because it's slightly difficult because it's on a different planet. So we need to use slightly different techniques than we would up here, for example, to work out what mineralogy is here. And the last thing is Earth's magnetic field behavior. So when these rocks form, they actually record the history of the Earth's magnetic field. Sorry, not rocks on Mars are not going to do that, but the rocks here will do that, okay? And even bacteria do it as well. So by understanding the mineral physics and how these things are magnetic actually helps us to understand how Earth's magnetic field has evolved through geological time, how it protects us from things like the solar wind, and so on. Okay? So that's another thing that I'm working on. So that's how we really go from this atomic to planetary scale. So like I said, I'm not going to mention specific projects, but if you're interested in the kind of work that I'm doing, a bit more information with the QR code there, or just come check. Okay. Right. Who's next? Chris.
Yes, hello everyone. My name is Grace and this is Sia, and our names are they're there also on the last slide. But we're broadly representing a group who do something with geodynamics. So this is something that's generally looking at the solid Earth, but it doesn't just stop or start with the solid Earth. It's how it interacts with the other spheres like the biosphere, the hydrosphere, cryosphere, and so on and so forth. And to do that, we look at a range of different temporal and spatial scales. So everything from present day to thousands to millions and billions of years in the past. But also on spatial scales that range from, atomistic through to basin scale or hand samples, basin scales, and even planetary elements. So we're generally cycling between some sort of time and space research. The toolbox that we have to do this kind of research is very diverse. And we get to work with a lot of different people here at RSES and more broadly. So we're looking at integrating, for example, maths, chemistry, and physics to answer some problems. We look at observational data, so going out and collecting things or using information that's available, including geology, geophysics, and geochemistry. But we also run a lot of computational models, which we'll explore in the next couple of slides. And a couple of the software programs that we use and in many cases develop here at ANU, including Gplates, Geodopt, and Underworld, can be used to answer some of these questions. So we don't have specific topics that we're going to show, but more of the research themes. So if you have any interests specifically, come and have a chat to us. So kind of on the more bigger picture end of the geodynamics research, we look at, for example, crustal and lithospheric architecture, for example, how it might link to the distribution and quality of different minerals. We do a lot with plate tectonic reconstruction. So for example, I'm looking at a project on the formation of the east coast of Australia. And then we also have some models, what's an animation that should run, there we go, of mantle convection. So you can see these blue blobs and these red blobs in the mantles, looking at, for example, subducted slabs of oceanic lithosphere or massive mantle plumes that might cause volcanism. I'm going to pass over to Sia.
Hello, everyone. My name is Sia. First of all, you might have been confused by the name Grace. I got Grace here. One of them is the satellite that Paul talked about. One of them is a sophisticated model like system for detecting gravity. The other one is obviously the satellite.
I also have my own gravitational.
So, as Grace mentioned, we are representing a diverse group. We have projects that work together. We thought we'd just put all of these together. And it's mainly about the solid Earth, but different components of solid Earth. So on the left-hand side, what you see is there's a cartoon representing groundwater. And you might have listened to Paul talking about the the changes in gravity, how we can compute that to changing volume of water. And groundwater represents the biggest portion of the water budget, more than 90% most of the time. So if we don't observe something at the Earth's surface and we know there is some gravitational change, the whole key is how can we just model the subsurface flow? And this is one of the things we do. This research works with Paul. We have cross collaboration with all, which is just looking at these models and trying to basically put together data and models in order to do data simulation, in order to build models that are more reliable, in order to forecasting, also understanding different groundwater systems. The other research that we put it on the geodynamics, but generally because of the you might have heard about sea level. Adele mentioned one of the biggest uncertainties about sea level by the end of this century is how much, for example, Antarctica is going to produce, how much Antarctica is going to produce. Now, one of the key ways to look at that is just go through the geologic history and see, okay, what is the estimates that we have for greenhouse gas emissions? You know, just go to the record and see when was the last time we had comparable values, look at sea level. And when we look at those records, we see that the records are all over the place. Now, that is the point that we start about thinking about the effect of solid Earth. So solid Earth is not that solid, different timescales, it moves up and down, depending on different forces. It might be a block of ice that might just push things down, and when it melts, you might rebound. It might be plate tectonics. When it moves inside the Earth, it's going to generate forces that think they're going to go after that. And this is well documented in the geology. So one of the ways we do that, we also do data simulation with one model, and we look at the predictions that they have for sea level change, and what then we compare this with current records in history. This can happen on geologic timescales, like millions of years. This could happen on what we call the scholastic time frame, which is like thousands of years. And we basically try to look at these different processes. And that is all say there's a lot of cross collaboration. The people that are, and these are the research represented by I'm representing for Louis and all the geoanalysis at RSES. There is a range of processes, from looking at mantle convection, forces within the mantle, looking at surface processes, how, for example, landscapes evolve. Why do we have different valleys, different mountains that erode, and so on. We can look at dynamic forces from plate tectonics, for example, earthquake rupture, how they happen, and what are the processes that they evolve, and generally you get fluid dynamics sort of problems in general versus, so as you can see, landscape tectonics and subsurface. Now, bunch of people. Roger Davis, Louis Parisi, you might have seen from different courses. That's me in the middle, Grace to the right, and Mark Hogarth, who's currently in the hospital because of the operation he had. He removed his appendix, but there are a bunch of like early career researchers that are very fun to work with. Generally, the topics have a wide range from math, pure math, to applied math, to physics. Lots of high performance computing. If you are interested in using the supercomputer here, there are lots of fun projects. Also, there are lots of observational projects that works with geodesy, geology, so on. Yeah, these are the people. Please come to talk to us if you have any questions. Thank you.
Good morning, everyone. My name is Sun. I'm here to present the group Global and Planetary Seismology Group. Our group leader is Havoy, who's not cannot be here today due to a college level duty. In our group, we are looking at we analyze seismic waveform or ground motion record to understand using different mathematical tools to understand how the Earth system work in general. Here's a couple of slides that we show the diversity of our research group interest, including very deep into the Earth interior, looking at other planets, studying the dynamic of earthquakes, and also other man-made explosion. So in our group, which offer a wide range of research projects, including PhD, honor, master, and PhD level. Some of you here have already done a couple of projects with us. So in our research, we often work with numerical simulation or mathematical inference or signal processing to understand average wiggle in a seismic waveform. So those are examples of seismic waveform, filter different frequency band, and you can see at each frequency band, it can tell us about different property of either the source or the material the seismic wave propagate through. We're looking for students with a diverse background, and we hope that doing some research with us, all of those skills can be brought to life as others interesting projects offered by RSES. So this is one of the, in the following slide, we present a couple of research themes that our group is covering at the moment. Firstly, we look at seismic structure of the Earth at the planetary scale. So for example, we study the structure and dynamic of the Earth core. Here is the example of our discoveries a few years ago, where we find new evidence to prove there's an innermost inner core within the inner core, for example. Another study, we're looking at seismic data collected from the NASA InSight mission. And so that there's the liquid core within the red planet. Another project is we are looking at using simulated waveform to study ice moon in preparation for future mission to those planetary bodies in the near future. Apart from studying the Earth structure, we're also looking using seismic data to understand the dynamic of the seismic source. We try to infer what we can learn from those data, and equally important, what we cannot learn. In other words, which is the uncertainty of the inverted parameter. So we have projects looking at the inference theories to how to best quantify the uncertainty of those source model. We also apply those theory to study earthquakes, volcano eruption, different man-made explosion, and also ice quakes. So ice quake is one of the topics that I'm myself interested in, where we use geodesical seismometer. There's a lot of them in Antarctica and in Greenland to study the internal structure of the ice shells. We also look at through the seismic signals that they generate. We study how they flow and they discharge iceberg to the ocean. All of those topics are pretty relevant to the context of climate change and global warming. So here's the personnel working on in our group. Who is group leader? This is myself. This is in the audience here, and Lily is the recent products in our group. So if you are interested in any aspect of the research, please come and to talk with us or send us an email. Thank you.
Awesome, thank you. So that was all the presentations. I think we have about 2 minutes if there's some really quick questions before we need to hand over to EMS Society. Are there any questions? No? Okay. then please do, if you're interested in any of the projects, please catch up with the people who advertise them, drop them an email or drop by their office. And yeah, thank you for coming.
Why bring fuel lines?
Thanks, Callum.
Yeah, that was the.
Where's that?